Hi, I'm Martina Costa Angeli. I'm a postdoc at the Sensing Technology Lab of the Free University of Bolzano in Italy. And I'm going to present you a work entitled Assessing the Role of Textiles in the Performance of Wearable Screen Printed Strain Sensor for Breathing Rate Monitoring. This work is a part of a European project entitled Textiles. In recent years, wearable, stretchable and non-invasive sensors for the continuous monitoring of the physiological parameters, for instance, the cardiac activity, the breathing and biomarkers in the sweat, have attracted interest not only for the medical diagnosis but also in sports. Specifically for sports, it is interesting the possibility to continuously monitoring the breathing, which can be used as a biomarker for the physiological status of an athlete. The breathing rate can be easily measured using a simple resistive strain sensor that is placed around the subject's chest and that is able to measure the expansion, the contraction of the rib cage and the abdomen, and so detect the respiratory cycle. In this perspective, we decided to realize a wearable non-intrusive screen-printed resistive strain sensor in a cost-effective and easy fabrication process. The sensor was realized by firstly performing a screen printing of a commercial cardboard paste on a stretchable TPU substrate. Then the sensor is encapsulated in order to protect it from the external environment. Then it is shaped to the desired shape and laminated onto the textile. An example of this as-fabricated sensor is presented in these slides. In collaboration with the partners text market, we decided to characterize two different textiles that are commonly used for cycling t-shirt. Chrono, that is made of polyester-based thread, and Asteria pesante, which is characterized also with a small percentage of a stretchable thread elastan. As concerns the sensor geometry, a U-shape was chosen because it has a compact structure that also ensures an easy way to connect the sensor with the readout system in the real application. And two different widths of the sensor were tested, 5 mm and 2.5 mm. The sensor was characterized performing cyclic electromechanical test at 0.2 Hz that corresponds to 12 breaths per minute and which mimic the quiet breathing, applying a maximum strain of 10% of deformation, which allows us to widely cover the strain range that the strain sensor will undergo in the real application. The results were evaluated in terms of resistance change, sensor stability and sensitivity. These two pictures show the resistance change for the sample characterized of the two textiles, Chrono in green and Asteria pesante in red, and the two widths, 5 and 2.5 mm. In the case of Asteria pesante textile, the peak resistance change decreased about 30% after the first 100 cycle, and then it stabilized independently of the sensor width. The initial drop in resistance is typical for textile-based printed strain sensor, which could be ascribed to the mechanical stabilization of both the fabric and the sensor when it is respectively stretched. Instead, for us concerned Chrono, the resistance shows a smaller and faster reduction, and then it's followed by a continuous drift without stabilization up to 1000 cycles. If we give a close look to the resistance change in function of the applied strain, we can see that interestingly, besides the first stretching cycle that showed a resistance peak shoulder in the correspondence to the maximum applying strain, 10%, the further cycle showed a second peak higher to the first one in the correspondence of the strain of 0%. A similar phenomenon was also reported in other works, and it can be explained by the mechanical hysteresis effect and the viscosity of the sensitive material and the polymeric substrate. Indeed, if we give to the sensor more time to relax with a hold time of 15 seconds, the sensor shows only one peak in correspondence to the 10% of strain. Considering the sensitivity that is calculated as the resistance change normalized, we can see that the two textiles are characterized by a different behavior, and this differences is related to the different stretchability, also if compared to the stretchability of the TPU substrate. Indeed, as the image on the right side shows, the sample is characterized by a non-homogeneous deformation pattern. The area of the textile not covered by the sensor was subjected to a more stretching. Instead, the U-shaped sensor, since is stiffer due to the presence of the TPU substrate, was subjected to a deformation lower than the nominal applied, correspond to 10%. This phenomenon is more evident when the textile is characterized by a higher stretchability as the steria pesante, that indeed shows a lower sensitivity if compared to chrono. This finding is also proved by the fact that the strain sensor characterized by a lower sensor width is characterized by a higher sensitivity if we look at a steria pesante textile. Indeed, by decreasing the sensor width from 5 to 2.5, the sensor and so the TPU substrate cross-section decrease, leading to a stiffening reduction. Consequently, since the sensor is more stressed, the 2.5 mm wide U-shaped sensor shows a higher resistance change. Among all the results, we can conclude that the chrono-based sample presented the best performance in terms of sensitivity. However, since breathing is a cyclic phenomenon, sensor stability is a significant concern for this type of application. Thus, we decided to select the steria pesante 2.5 mm wide device as the most suitable textile sensor combination, as it provides a good compromise between stability and sensitivity. Finally, the selected textile sensor combination was evaluated on a healthy male performing a preliminary test during rest. The U-shaped sensor was integrated into an steria pesante textile strip and placed around the subject abdomen on the axillary line. As shown in the figure on the right, the sensor was able to follow the breathing pattern with a resistance change similar to that reported in the electromechanical test. In conclusion, with this work we characterized and compared the performance of a wearable screen-printed low-cost strain sensor on two different types of textile. The electromechanical test highlighted the importance to evaluate the mechanical behavior of the materials employed in the design phase and allow us to select the most suitable textile sensor combination for the specific application. Moreover, a test performed on a human subject indicated the possibility to use this sensor for breathing rate measurement. More research is needed to fully characterize this sensor, in particular to integrate the sensor into a t-shirt and validate it through human trials. This work was funded by an European-funded project called STEX and was realized in collaboration with other university industrial partners. Thanks for the attention.